All right, let's try an example for radioactive decay. So let's suppose we have this radioactive element, strontium-90, and we know the decay constant is lambda, which is equal to 0.0244, and we're measuring time in years. And what we want to answer here is how long will it take for just some quantity, P of 0, of this strontium-90 to decay to 1/2 its original mass. So essentially what we want to find here is we want to find the half-life. So we want to find T such that the size of our population here is 1/2 our starting population. So P of T is equal to 1/2 times P0. All right, so we know that this is a radioactive element undergoing radioactive decay. So let's write down our exponential decay formula. And that is P of T is equal to P0 e raised to the negative lambda times T. And we know what lambda is. So we're going to set up our equation. And we're going to set up our equation based on what we're trying to find. So we know our population, we have this formula, and we want to set it equal to 1/2 of our starting population. So we're going to set 1/2 times our starting population equal to just this formula. So P0 e raised to the negative lambda times T. Now we technically know what lambda is, so we could fill it in, but because it's a decimal, we'll wait until the very end to fill that in. And what we're trying to find here is T. We're trying to figure out T. We want to solve this equation for T. So let's work on solving this exponential equation. And it really just comes down to unraveling, trying to get all the terms over on this right side, get rid of them, move them out to the other side so we have T all by itself. And so the way we can do that is, well, first kind of start with this P0 that's in front. We want to get rid of it. So divide both sides of this equation by our P0. So when we do that, what do we get? Well, we're going to get 1/2 on the left. The P0s are just going to cancel. The P0s over here are just going to cancel. So kind of surprisingly, what we get is we don't actually know how much we're starting with, but it doesn't matter. So it takes the same amount of time regardless of how much material you actually start with. So we don't actually, in order to figure out the half-life, we don't actually, in this case, need to know how much material we start with, because we know what lambda is. If we didn't know what lambda is, then yeah, we'd probably need to know how much material, take some sample readings and how much, do some measurements, that kind of thing. But since we know the decay constant already, we can figure out the half-life without knowing the initial mass of our quantity here. All right, so we've gotten this equation, and now we want to unravel that exponential, get rid of this exponential, and we know the way to do that is with natural log. So we're going to apply natural log to both sides, and I left the space on the wrong side of the equal sign, or on the wrong side of the 1/2. So natural log 1/2, we apply natural log to both sides. And natural log and e, when they're right next to each other like that, we get to cancel them. That's always nice. And then simplifying this, we get negative lambda times t is equal to natural log of 1/2. And then finally, we want to solve for t. So to get t by itself, just divide both sides of this equation by negative lambda. And what we do is we get t is equal to natural log of 1/2 divided by negative lambda. And if we fill in what we know lambda is, we get natural log of 1/2 divided by negative 0.0244. And this is approximately 28. It's approximately 28. So if we were to do this calculation here, it's going to be approximately 28. And time is measured in years. So our half-life here is going to be years. So just make sure, using units. So this is our half-life, approximately. You know, technically this is our exact half-life. This is an estimate for, you know, for our half-life. So better to consider the exact value there, but just to kind of give some idea, we're talking 28 years for this particular element. All right, that's one of the games we can play, is if we know the decay constant, well, let's find the half-life. So we can turn it around, and we maybe know the half-life, and we want to find the decay constant. So we'll see that in the next example. We'll see you there.